So last time we discussed about particle in one-dimensional box, then particle in three-dimensional box. We also discussed about degeneracy using the results of particle in three-dimensional box. How to explain degeneracy, we have seen that. Okay, now let us discuss some more things about particle in one-dimensional box, then particle in two-dimensional box, then particle in three-dimensional box. Okay, so uh, let us first see particle in 1D box. Okay, let us first see particle in 1D box. So earlier we considered the system like this. Okay, one particle of mass m is moving in x dimension, moving along x dimension. The particle is confined between two potential walls. One potential wall is at x equal to 0. The other potential wall is at x equal to a. So that the length of the box is a. Okay. So we have seen this. Now when we take the box like this, x equal to 0, x equal to a, then generally we call it asymmetric 1D box. Asymmetric 1D box. Okay, one dimensional box. This is asymmetric 1D box. Okay, but if we take the limits like this, okay, let me draw separately. This is asymmetric 1D box, but if we take the limits like this, these are the two potential walls, one at x equal to minus a, the other at x equal to plus a. This is called symmetric 1D box. Symmetric 1D box. Okay, symmetric 1D box. Now as this is asymmetric 1D box, okay, and we have seen psi equal to, so psi depends on one quantum number, this is equal to this, and this is equal to half sine n pi x by a, and energy equal to n square h square divided by 8m a square. We have seen this. In case of asymmetric 1D box, we have obtained these two results, and here n equal to 1, 2, 3, etc. n equal to 1, 2, 3, etc. and n is the quantum number. Now in case of symmetric 1D box, what we get? In case of symmetric 1D box, what we get? We get psi equal to 1 by a whole to the power half sine n pi x by 2a when n is even. Even means it may be 2, 4, 6 like that. Okay, 2, 4, 6 like that. N is even. And this psi n. Okay, psi depends on n. And psi, this is equal to 1 by e whole to the power half cos n pi x by 2a when n is odd. N odd means 1, 3, 5, etc., etc. So it is like this. So for symmetric 1D box, psi equal to this when n is even, and psi equal to this when n is odd. Okay, when n is odd. And what about energy? Energy equal to, here energy equal to n square h square by 8 ma square. Okay, because length of the box is E. Length of the box is E. But here 0 will be somewhere here. 0 will be somewhere here. So length of the box is 2A. Length of the box is 2A. Okay, 2A. So here energy equal to n square h square 8m 2A square. Length of the box is 2A now. So this will be equal to n square h square by 32m a square. 32m a square. Okay. So these are the expressions. Okay, these are the expressions. But you remember, in general, when we say particle in one-dimensional box, we mean this asymmetric. I repeat, in general, when we say particle in one-dimensional box, we mean this. We mean this, not this. So, whenever some questions are asked in the examination stating particle in one-dimensional box, you consider this. Do not consider this. Do not consider symmetric 1D box. Okay? You consider this only. Alright? So this. Next thing, say one question has been asked, suppose. One question has been, okay, let me talk about degeneracy also. Degeneracy. So here we have only one quantum number. I am talking about this particle in one-dimensional box. Particle in one-dimensional box. Okay. N equal to 1, 2, 3, etc. Particle in one-dimensional box. That is asymmetric. Okay. So only one quantum number we have. We have only one quantum number. Okay. So energy depends only one quantum number. Wave function also depends only one quantum number. So for a particular value of energy, we will have one particular value of psi. Okay. Say n equal to 1. N equal to 1 equal to U, energy will be U1 and corresponding wave function will be psi 1. You can just put here. We have already seen. Okay. Similarly, when n equal to 2, energy will be E2, wave function will be psi 2. That means one energy level, one wave function. One energy level, one wave function. One wave function means one state, one state. So one energy level, one state. One energy level, one state. In each energy level, there will be one state only. So we can say that degeneracy in case of particle in one-dimensional box is 1. We can say like that. Actually, energy levels are not degenerate because with each energy level there is only one state. When we get degeneracy, if one energy level has more than one state, then we get degeneracy. So in particle in one-dimensional box, there is only one state in each energy level. So actually not degenerate. Still we can say that each energy level is one-fold degenerate. That means one energy level, one state. One energy level, one state. Like that. Okay. Now If you consider particle in 2D box, particle in 2D box, two-dimensional box, okay, particle in 2D box. Well, first let us talk about particle in 3D box, because we have discussed about this particle in 3D box. So what is the wave function? Wave function depends on three quantum numbers. Let me write it like this: nx, ny, nz. Okay, three quantum numbers. Wave function depends on three quantum numbers, and what are the values? Value is 2 by a over uh, 2 by 2 by a into 2 by a into 2 by a. So this is 8 whole to the power half, so it will be 3 by 2. Sin nx pi x by a sin ny phi y by b sin nz pi z by c. And here we have assumed that a equal to b equal to c. That means the box is a cube. Okay, that means symmetrical. The box is a cube, that is symmetrical. Okay, when we have a symmetric system just like a cube, we get degeneracy. Okay, and energy equal to and again energy depends on three quantum numbers. We may write like this: nx, ny, nz. We may write like this. So what is the energy? Energy will be equal to n square h square by sorry, not n square, h square by 8 ma square into nx square plus ny square plus nz square. Okay, nz square. Now here you see, when say nx equal to ny equal to nz equal to 1, then we have one energy value. We have energy value E11, okay, and that energy equal to 111, that is 3 h square by 8 m a square. Okay, and corresponding wave function will be this 111, and we will have only wave function. We have already written this. That means when nx equal to ny equal to nz, okay, we have one energy value and we have only one wave function. Okay, one energy value, one wave function. So this level is one-fold degenerate, because with this energy level there is only one state. Okay, one state. Similarly, when nx equal to ny equal to nz equal to 2, corresponding energy will be E222. Okay, that will be equal to 4, 4, 4. So 12. 12 into h square by 8 m a square. Okay, now once again we will have only one wave function, 2, 2, 2. We will have only one wave function. Okay, 2, 2, 2. So this will be sine 2 pi x by a, 2 pi y by b, 2 pi z by c. We will have only one wave function. That means one energy level, one state. Okay, one energy level, one state. Okay. But if we have like this, say if we have like this, say nx equal to 1, ny and z equal to 2, okay, and z equal to 2, then we will have energy sorry uh, 1, well, this will also, this, say, let me write it like this, ny equal to 1 and nz equal to 2, nz equal to 2. So energy will be equal to 112, and this will be equal to how much? This will be equal to 4 5 6 6 6 h square. Energy will be equal to 6 h square by 8 m a square, and corresponding wave function will be psi 112, okay, psi 112, that will be equal to 2 by a whole to the power 3 by 2 sine pi x by a sine pi y by b sine 2 pi z by c, okay. Similarly, if nx equal to 2, ny and z equal to 1 and z equal to 1, so we will have same energy, that is 6 h square by 8 m a square, and wave function is psi 211, so this will be 2 by a whole to the 3 by 2. Now sine 2 pi x by a sine pi y by b and sine pi z by c, okay. Similarly, nx equal to nz equal to 1, but ny equal to 2, okay. So energy will be same, 1216 h square by 8 m a square, and corresponding wave function will be 121 2 by a whole to the power 3 by 2 sine pi x by a sine 2 pi y by b and sine pi z by c, okay. So they represent three different states. We have already said they represent three different states, because this is twice along z, this is twice along x, this is twice along y. So they represent three different states, but they are having the same energy. So this energy level is threefold degenerate, because there are three states. So this energy level is threefold degenerate. Okay, threefold degenerate. Okay. So we have already shown using diagram like this. Okay, so this is a energy E111. With this energy there is one state, psi 111. With this energy there is one state. Now this is a 6, E211, 6 into this, okay, 6 into this. So there will be three states. Psi 211, psi 121, and psi 112. So this energy level is threefold degenerate. threefold degenerate. Okay, then again again say E222. Okay, this energy level again 1. We have only one wave function, and so on. So you see, again, if it happens like this, say nx equal to ny equal to 2, nz equal to 1, nz equal to 1, then we will have energy value 2 to 1. Corresponding wave function will be psi 2 to 1. Okay, but uh, same energy value we may have wave function like this, say 2 1 2. Energy value will be the same, energy value will be the same. We will have another wave function, say another wave function we may get 1 2 2. So you see, again this energy level will be 2 to 1. This energy level will be threefold degenerate. Okay, threefold degenerate. And what is the value? 4 4 10 11. So that will be equal to 11 h square by 8 ma square. 11 4 4 sorry 9, not 11 9, not 11 9. Okay, 4 2 2 4 4 1 9 9 9. This energy level will be equal to 9 into this. So this energy level will be equal to, it will be threefold degenerate. Say suppose this is 2 to 1 2 to 1. So this energy level will be threefold degenerate. 2 to 1 psi 2 1 2 psi 1 2 2. This energy level. Again this energy level, say E2 2. This energy level is one fold degenerate. So in general we can say that if nx equal to ny equal to nz, in case of 3D box, that is cube, in case of cubic box, if we have like this, if we have a condition like this, then that particular level, that particular energy level, E, nx, ny, nz, that particular energy level will be one fold degenerate. If the three quantum numbers are the same, then that energy level will be one fold degenerate. That means we will have only one state, that is one wave function. Now if nx equal to say ny but not equal to nz, or it may happen that as a nx equal to nz not equal to ny, then such energy levels will be threefold degenerate. Okay, so if this be the condition, two quantum numbers are same but one quantum number is different, then that energy level will be threefold degenerate. We have already seen this. But if nx is not equal to ny, is not equal to nz, then that particular energy level will be sixfold degenerate. Let us take an example. Say suppose nx equal to 1 ny equal to 2 and nz equal to 3. Okay, so we will have one energy value E 1 2 3. We will have one energy value, but how many wave functions we will get? We will get one wave function like this, nx1 ny2 nz3, or it may be like this 1 3 2 nx1 ny3 nz2. It may be like this. Okay, then we will have this 2 1 2 1 3 2 1 3, or we may have this 2 3 1 nx ny nz. Okay, then we may have this psi 3 2 1 or psi 3 1 2 nx ny nz. So we will have 6 wave functions. That means we will have 6 states. So in this case, the energy level will be 6-fold degenerate if all the 4 quantum numbers are not the same. Okay. Then let us consider particle in 2D box. Particle in 2D box. This is not included in your syllabus, so don't worry. But let me talk about this also. Particle in 2D box. So here, here wave function will be say 2 by a whole to the power half sine nx pi x by a and sine ny 2 by b whole to the power half ny pi y by b. Okay, this. So energy value will be equal to h square by 8m nx square by a square plus ny square by b square. So similar to 3D box, exactly similar to 3D box. In case of 3D box, we had one more term nz square by c square. Okay, here also we had one more term sine nz by z by c. Okay, so 2D box means we have this. Okay, this is the x-axis, this is x-axis, and this is y-axis. Again here v is 0, outside v is infinity. Okay, this is 2D box. Now if the 2D box is a square, square means a equal to b square. Then we will have psi equal to 2 by a. Okay, because same 2 by a sine nx pi x by a and sine ny pi y by, we may write a or we may write b, because a equal to b, and energy will be equal to h square by 8m a square nx square plus ny square. Again here nx equal to ny equal to 1 2 3 etc. Okay. So here also you may have degeneracy. So suppose um, nx equal to ny. If nx equal to ny, okay, then we will have one energy value, and correspondingly we will have only one wave function, only one wave function. Okay, suppose this is equal to 1, this is equal to 1, so we will have e 1 1, and correspondingly we will have psi 1. So one energy value, one wave function. That means in this case degeneracy will be 1. In this case nx equal to ny, in this case degeneracy will be equal to 1. But if nx is not equal to ny, is not equal to ny, then what we will have? Suppose nx equal to 1, suppose nx equal to 1, ny equal to 2. Okay, so we will have energy E1 2, which will be equal to E2 1. But wave function we will have 1 2 and 2 1. That means two different states, one energy level, two different states. So this particular energy level will be twofold degenerate. Okay, so this is degeneracy. Let me write degeneracy as Z. Z means degeneracy. Here degeneracy is 1, nx equal to ny, but here degeneracy equal to 2. Okay, nx is not equal to ny, degeneracy equal to 2. Okay, all right. So this is all about degeneracy. Now let us see another problem related to particle in 1D box. Say you have been asked to say calculate question. Okay, calculate the probability of finding the particle in 1D box within 0 less than equal to x less than equal to a by 2. So you see particle in 1D box, that means it is asymmetric. So in general particle in 1D box, that we mean asymmetric. That means limit of the box is from 0 x equal to 0 to x equal to a. So this is the box. This is the box, x equal to 0, x equal to a. So we have to find out the probability within this range. This is a by 2. Okay, this is a by 2. So within this range, what is the probability of finding the particle? We have to find out. Okay, so how to do that? We know that probability equal to psi square. Okay, psi square dx. Probability equal to psi square dx. Okay, and here limit is from 0 to a. Limit is from 0 to a. Now we know psi equal to, we know the value of psi. Okay, what is the value of psi? Psi is equal to 2 by a whole to the power half sine n pi x by a. So we know this. Okay, so if we write this constant, we can take it out. Square will be this. Then 0 to a sine square. It will be sine square n pi x by a dx. So it will be this. Now, this type of calculation we have already done. We can write it like this. So 0 to a, 1 minus, so 2 sine square. Okay, I bring here 2, so this will be 2 sine square. This will be cos 2 n pi x by a dx. Okay. Then we have already done this type of calculation, so this will be 1 by a 0 to a dx minus 0 to a cos 2 n pi x by a dx. Okay. So this will be equal to, and this will be equal to 1 by a 1 by a into, this is a minus, this will be equal to a by 2 n pi, a by 2 n pi, this will be sine 2 n pi x by a 0 to a 0 to a. Okay, this is 0 to a. Oh, sorry, I have committed one mistake. So limit has been given from 0 to a by 2. So we have to find out the probability within this range, 0 to a by 2. So this will be a by 2. Okay, this will be a by 2, this will be a by 2. So we have to find the probability within this region. Okay, a by 2, because we have been asked to find out the probability from 0 to a by 2. So 0 to a by 2. Okay, within this range. So so this is equal to 1 by a, this is a by 2 minus a by 2 n pi, and when you put this limit, what happens? This is a by 2 n pi, sine n pi equal to 0. Okay, then this 0, so it will be 0 minus 0. Okay, so this will be equal to half. Okay, this will be equal to half. Half means, so probability will be equal to, so probability will be equal to 0.5, and that is equivalent to 50%. Probability equal to 0.5 or 50%. Okay, so so this way you can solve the problem. Well, now let us discuss about one more system, which is one-dimensional harmonic oscillator. One-dimensional harmonic oscillator. Okay, this is a new system. We have discussed particle in one-dimensional box. We have discussed particle in two-dimensional box, three-dimensional box. Okay, now we have to consider one-dimensional harmonic oscillator. Okay, now let us first see the classical picture. Okay, classical picture. Now, in classical physics, what is a harmonic oscillator? Say we can consider a very simple system. Say pendulum, suppose this is pendulum. Okay, pendulum. It is oscillating along x dimension. Okay, x dimension it is oscillating. Now, for one dimension, this amplitude should be This should be 4 degree. This should be 4 degree. Huh? This should not be greater than 4 degree. Then we will have the amplitude. We will have the amplitude. Okay. So this is one dimensional harmonic oscillator. It is oscillating. It is oscillating in x dimension. Okay, this is the x dimension. Oscillating in x dimension. Now here you see, say when the oscillator comes to the amplitude, at the amplitude, this is 4 degree. 4 degree. When the oscillator comes to the amplitude, then here kinetic energy is 0, potential energy is maximum, because it is coming like this, then it stops here, then comes back, again stops here, again goes back. Now it is moving like this. It is moving like this. Okay, so here the oscillator, the pendulum stops. So kinetic energy is 0. So here potential energy is maximum. Then it comes back. Here potential energy is 0. Kinetic energy is maximum. Again potential energy again increases. Here potential energy is maximum. Kinetic energy is 0. So you see, potential energy maximum, potential energy decreases 0, potential energy 0, increases maximum, potential energy again decreases 0, again increases. So here potential energy fluctuates. Potential energy fluctuates. Potential energy maximum decreases 0, again maximum, again decreases 0, again maximum. So potential energy fluctuates. Here potential energy is not 0. In particle in one-dimensional box or in particle in three-dimensional box, we assumed that potential energy is 0. But here potential energy is not 0. Neither it is constant. Potential energy is 0 নহয়, constant নহয়. Potential energy is neither 0 nor constant, but it fluctuates. Okay, কম বেশি হয়ে আছে potential energy. I repeat, maximum potential energy decreases 0, potential energy maximum, so potential energy fluctuates. Okay, kinetic energy also, kinetic energy 0, increases maximum. Okay, then kinetic energy decreases 0, increases maximum, decreases 0. So both potential energy and kinetic energy fluctuates here. Okay, so here total energy of the pendulum is a sum of kinetic energy and potential energy. Total energy is a sum of kinetic energy and potential energy. Okay, so important thing here, potential energy is not 0, neither it is constant. Okay, now in case of this pendulum, as it say this is equilibrium position, x is 0, this is equilibrium position, x is 0. Okay, here say x is positive. Displacement is a vector quantity. Okay, displacement is a vector quantity. Here displacement is positive, say here displacement is negative. Okay, it is a vector quantity. So displacement along positive direction, displacement along negative direction. So when it moves, kinetic energy decreases because there is a restoring force. There is a restoring force. Due to this restoring force, kinetic energy decreases, becomes 0. Then it comes back. Again here, kinetic energy increases, kinetic energy decreases, becomes 0. Why? Because there is a restoring force. And that restoring force F is proportional to displacement. If displacement is along this direction, direction of restoring force will be opposite. Okay? Direction of restoring force is opposite. If displacement is in this direction of restoring force will be opposite direction. Okay? So displacement along this direction, restoring force this direction, opposite. Therefore, we write it like this. Restoring force is proportional to displacement, but minus, because directions are opposite. Okay. We can write that F equal to minus kx, where k is a constant and is called the force constant. It is called the force constant. Okay. Force constant. Now, you also know, you have also seen that force equal to minus dv dx, where V is the potential energy. V is the potential energy. So you know this. So from these two, what we can write? We can write that dv by dx equal to kx. And if we integrate, we will get this. V, we can write dv equal to kx dx. So if we integrate, we get V equal to half kx square. If we integrate, we get a constant, but we are neglecting the constant here. Okay? We get a constant, we are neglecting the constant. So we get potential energy equal to this. Okay? Potential energy equal to this. Now if you draw a graph, say along this direction potential energy increases, and this is x. Okay, x. Here x is 0, equilibrium position. Here x is 0, so potential energy is 0. Potential energy is 0. Okay. Now potential energy increases because x has a displacement. Maximum displacement is the amplitude. Maximum displacement is the amplitude. So no doubt, as x increases, potential energy increases, no doubt, but there is a limit. Okay, so we will get a graph like this. Parabola. We get a parabola like this. We get a parabola like this. Okay, and this is the amplitude. Okay, this is the amplitude. This is a plus a, and this is minus a. This is minus a. Okay, this is minus a. So amplitude. So we get a parabola like this if we plot potential energy against displacement, because whether it is plus a or minus a, potential will be the same, potential energy will be the same. So we get a graph like this. Okay, so this is the potential energy. This is the potential energy for simple harmonic oscillator. Then also we get an expression, we can find out expression like this. Okay, we find out an expression like this, say x equal to a sine k by m whole power half into t. Okay, force constant by mass time. Okay, we get an expression like this. We get an expression like this. And total energy, we get an expression for total energy. We get an expression for total energy that will be equal to half k a square. Okay, because here you see x equal to a, so x equal to a means we get energy half k a square and here total energy will be equal to potential energy, because here kinetic energy is 0. Here kinetic energy is 0. At amplitude kinetic energy is 0. So total energy equal to potential energy. So we get this total energy. That means total energy is constant. Because amplitude is constant, so total energy is constant. So this is the classical picture. This is the classical picture of simple harmonic oscillator. So we are not interested in classical treatment. So we will discuss quantum mechanical treatment. Okay, quantum mechanical treatment. So quantum mechanical treatment. So we consider one particle of mass m executing simple harmonic motion. Okay, motion in x dimension, because we are considering one dimensional harmonic oscillator. One particle mass m, it is executing simple harmonic motion in x dimension. So particle is moving in x dimension. So what is the Schrödinger's equation? Schrödinger's equation, that will be equal to minus h bar square by 2m d2 psi dx square plus v psi. What is the v here? Half kx square. V equal to half kx square psi, and this is equal to E psi. So this is a equation 1. This is equation 1. Okay, one particle executing simple harmonic motion in x dimension. So for the particle, Schrödinger equation is this. Or we can simplify, say dividing both sides by this, and bringing together. So what we get? d2 psi by dx square plus h bar square by 2m e minus half kx square psi equal to 0. So what we have done? We have divided both sides by this and bringing this term to this side. We get this. Okay, this is the equation 2. Okay, so we are getting. Now in this system, what happens? I have already said, in this system potential energy is not 0, neither it is constant, but potential energy fluctuates. Okay, so in this case, in order to solve this equation, we use polynomials. Okay, so this is say a plus b whole to the power n. So this is a polynomial. You can expand like this: a to the power n plus n c1. Okay, a to the power n minus 1b, and so on. You can expand like this. So this is a polynomial. So in order to solve equation 2, we make use of polynomials. Okay, we make use of polynomials. But in order to use polynomials, we need pure number. Okay, we need pure number. So if you see, say, length of the bands. Length of the bands is, say, 2 meter. 2 meter. Okay, length of the band, say, 2 meter. So how we can write it? 2 into 1 meter. Now this is the value, this is the physical quantity. L, length is the physical quantity. Value is this. So I can write it like this. Here 2 is the pure number and this is the unit. 2 is the pure number, this is the unit. Okay, this is the unit. So we will use polynomials here, but in order to use polynomials we need pure number. But here x is not a pure number, it has dimension. X is not a pure number, it has dimension. So in order to solve equation 2, in order to solve two, what we do, we convert this equation. We convert this equation into a dimensionless form, dimensionless form. That means for x we have to use some dimensionless quantity. Here x has the dimension of meter in SI. X has the dimension of meter in SI. But in order to solve this using polynomials, in order to solve this equation, we have to use some dimensionless quantity in place of x. Okay, that means we have to, we replace x by some dimensionless quantity, say xi. So xi is the, say, dimensionless quantity. Okay, so we have to replace x by xi. Xi is the dimensionless quantity. Now we must have a relation between xi and x. We must have a relation between xi and x. So relation is that such that say xi equal to alpha x, where alpha is constant. So we will make this substitution. Okay, this is the equation 3. Now in this equation we have d2 psi by dx square. So in place of d2 psi by dx square, we have to write d2 psi by d xi square. Okay, we have to write d2 psi by d xi square. Similarly here also, x is to be replaced by xi. Okay, so how to do that? You see, we have d2 psi by dx square. So what we do? We write d psi by dx. Okay, this we can write like this: d psi by d xi into d xi by dx. Okay, we can write like this: d xi cancel, so we get this. Then from this, what we get? D psi by dx. D psi by dx will be equal to alpha. So this will be equal to alpha into d psi by dxi. D psi by dxi. Okay, we get this. but we have d2 psi by dx square. So d2 psi by dx square, and that is nothing but d dx, d psi dx. Okay, so d dx, I can write it like this: d d psi into d psi dx, d dx. So we can write like this into d psi dx, d psi dx. I can write this d psi dx equal to this. So alpha into d psi d psi. Again, d psi dx equal to d psi dx equal to alpha. D psi dx equal to alpha. So this will be equal to, this is equal to alpha. Alpha. So what we get? We get alpha square. We get alpha square because alpha is a constant. We can take it out. D2 psi by d psi square. D psi square. Okay. So for d2 psi dx square, for d2 psi dx square, we can write this. Now substituting this value into what we get? Alpha square d2 psi d psi square, plus h bar square by 2m e minus half k. For x, what we can write? For x, xi by alpha, x equal to xi by alpha. So this will be xi square by alpha square psi, that is equal to 0. So we can write this. Okay, or we can still simplify d2 psi by d psi square, we divide by alpha square, so this will be equal to h bar square by 2m alpha square e minus half k psi square by alpha square psi equal to 0. Or we can write d2 psi d psi square plus I can write it like this: h bar square by e 2m alpha square, okay, 2m alpha square. Oh, what have I done? This is 2m. This is 2m by h bar square. Sorry, I have divided. So this is 2m by h bar square. What have I done? 2m by h bar square. 2m by h bar square. Okay, 2m by h bar square, or d2 psi by d psi square, plus 2me by h bar square alpha square, okay, minus 2 cancel m k mk by h bar square alpha to the power 4, alpha to the power 4, uh, alpha to the power 4, okay, into xi square psi equal to 0, okay, 0. Now say alpha is a constant, alpha is a constant, we choose like that, um, we choose like that mk by h bar square alpha 4, we choose this to be 1, we choose this to be 1, so that alpha to the power 4 equal to mk by h bar square, and so alpha becomes equal to this 1 by 4. So alpha is a constant. If we take this value, mass of the particle, this force constant h bar, so if we take alpha this to be equal to, because alpha is a constant, we can choose the value of alpha. So if we take value of alpha to be this, then this will be equal to 1. Then this will be equal to 1. Okay? This will be equal to 1. So, um, so thus what we get? Thus what we get? Uh, d2 psi d xi square plus this value is constant, mass particle constant, E constant, this constant, this constant. So we replace this by one constant, say lambda, and this is 1, so this is xi square psi equal to 0. This is the equation number 4. This is equation number 4. So you see, what we have done is that we have replaced x by xi. And what is xi? It is a dimensionless quantity. It is a dimensionless quantity. So we do not need the detailed mathematical calculations, and after this we will just write the result. Okay, this I have done just to show how xi comes. Okay, so up to this we have done some calculation, but after this we don't need any calculation. Okay, that means initially we were supposed to solve this equation. This equation or this equation. So initially we were supposed to solve this equation or this equation. If we solve this equation, we will get the value of psi in terms of x. Okay. Now we have converted this equation. Okay, to this. We have converted equation 1 to this equation, where x has been replaced by xi. So if we solve this equation, we will get the value of psi in terms of xi. But if we get the value of psi in terms of xi, we can convert it in terms of x, because we have got the relation. Okay. So now we will just write the result. Now solving equation 4, no? From equation 4. Solving equation 4, we find that psi, the wave function depends on one quantum number, which is v. Here v is the quantum number. Wave function depends on, solving equation 4, we find that the wave function depends on one quantum number, which I represent as v. Okay, v, and that will have one normalization constant. Normalization constant will always be there. Okay, in quantum mechanics, we will always have a normalization constant, and here we get one thing which is called, this is called Hermite polynomials. Okay, this is called Hermite polynomials. So I talked about uh, Hermite polynomials. I have already said that we solve the equation by using polynomials. So this is the symbol, this is the symbol for a polynomial which is called Hermite polynomial. Mind that this is the symbol only, symbol only. And then we have function like this, xi square by 2, xi square by 2 e to the power. So this is the value of psi. Okay, this is the value of psi we get. And what is the value of normalization constant? Value of normalization constant is this. So psi, I can write like this, psi v xi, because we are getting the value of psi in terms of xi. Okay. What is the value of normalization constant? Value of normalization constant is this, alpha pi to the power half, pi to the power half into factorial v, factorial v into 2 to the power v, 2 to the power v whole to the power half. This is the value of normalization constant. This is normalization constant. This is the value of normalization. Alpha pi to the power half factorial v into 2 to the power v whole to the power half. And this is h v xi Hermite polynomials and e to the power minus xi square by 2. So this is the value of the wave function. Okay, and we get the value of energy also, because whenever we solve Schrdinger equation we get two things, wave function and energy. Energy is this, v plus half h omega oscillation. What is omega oscillation? It is oscillation frequency, because particle is executing simple harmonic motion like this, particle is executing simple harmonic motion like this. So this is the frequency of oscillation, frequency of oscillation, that is number of oscillation per unit time. One oscillation, two oscillation, three oscillation, like that. Number of oscillation per unit time, oscillation frequency. And that is equal to 1 by 2 pi root over k by m, k by m. Force constant, not Boltzmann constant, it is force constant by mass of the particle. So this is, now here we are getting one quantum number. So we have one variable x, and correspondingly we are getting one quantum number v. Now here value of v may be 0, 1, 2, 3 and so on. Value of v may be this. Okay. Now say we have said that this is Hermite polynomials, this is Hermite polynomials, and this is the symbol, this is the symbol. For Hermite polynomial we have one expression, the expression is like this, whole to the power v, v is the quantum number. Let me see the expression. Okay, let me see the expression. E to the power into e to the power xi square into e to the power xi square dv d xi v e to the power minus xi square. Okay, this is the expression for Hermite polynomials. This is the expression for Hermite polynomials. Okay. Now let us see how to find out wave function and energy. Now if v equal to 0, if v equal to 0, so you see energy is 0. E naught, v may be 0, but energy is not 0. In particle, in one-dimensional box or three-dimensional box or two-dimensional box, we obtain the quantum number. But there we have seen that quantum number cannot be 0. But here we find that the quantum number may be 0 as well. Now, why this is possible? Right now we do not know because we have not done the detailed calculation. Okay? If we do the calculation in detail, we will know why v can be 0 also. But let us ignore that. Let us ignore that part. Let us assume that, let us take that v may be 0 also. v0, 1, 2, 3, etc. So on. Okay? So v may be 0, but this energy is not 0. This is equal to half h omega oscillation. Okay? So correspondingly, we get one wave function psi 0 xi. So what is the value? Value is alpha pi to the power half factorial 0. Factorial 0 equal to 1. 2 to the power 0, 1. Factorial 0, 1. 2 to the power 0, 1. So this is equal to alpha by pi to the power half whole to the power half. Whole to the power half. Constant, this constant. Then h0 xi. Okay? h0 xi into e to the power minus xi square by 2. Xi square by 2. Okay? Now let us see what is h0 xi. h0 xi. This is the expression. So minus 1 to the power 0, that is 0. Okay? Minus 1 to the power 0, that is 1. So this is 1. E to the power xi square, d0, 1. So this is 0 into e to the power minus xi square. So e to the power x, e to the power minus x equal to e to the power 0, that means 1. So what is psi 0 xi? Psi 0 xi, that is equal to alpha pi to the power half whole to the power half into e to the power minus xi square by 2. Xi square by 2. Okay? This. Now if v equal to 1, then energy equal to v plus half. That means it is 3 by 2 h omega oscillation. Okay? Corresponding wave function psi 1, that is equal to alpha pi to the power half, then factorial 1, 1, 2. 2 to the power 1, 1. 2 to the power 1, 2. Whole to the power half. Then h1 xi. h1 xi into e to the power minus xi square by 2. h1 xi. Okay? h1 xi. Minus 1 to the power 1. That means it is minus, okay, alpha 2 pi to the power half whole to the power half, that is minus 1 to the power 1 e to the power xi square, okay, e to the power xi square into d xi Okay, and let me write separately. Okay, let me write separately. H1 jai, H1 jai equal to minus 1 d minus 1 e to the power jai square d jai e to the power minus jai square okay, minus 1 e to the power jai square. Now d dx e to the power x, d dx e to the power x equal to e to the power x, e to the power x into 2 jai. Okay, this is minus 2 jai. d dx of this equal to first e to the power x, then d dx of x square, no, x. So we get this. So this will be equal to, this is 1 e to the power 0 1, so this will be 2 jai, 2 jai. Okay, 2 jai. So psi 1 equal to alpha 2 pi to the power half whole to the power half 2 jai into e to the power minus jai square by 2. Okay, so we are getting this. So energy equal to this, and we are getting this psi 0. Okay, psi 0 and energy this. So energy this corresponding wave function this, energy this corresponding wave function this. Similarly, we can find out, say, if v equal to 2, so energy will be equal to 5 by 2 h omega oscillation, and corresponding wave function psi 2 jai. So that will be equal to first constant alpha pi to the power half 2 to the power v, that means 2 square, 2 to the power v, that means 2 square, factorial 2 means 2, whole to the power half, and h 2 jai into e to the power minus jai square by 2. Now once again h2 jai that is equal to minus 1 square, that is 1, then e jai square into d2 d jai square e to the power minus jai square, and that is equal to e to the power jai square d jai into d jai e to the power minus jai square. Okay, jai square. So if we simplify this, e to the power jai square d jai, okay, d jai, then this will be 2 minus 2 jai into e to the power minus xi square, e to the power minus xi square, or this is equal to minus 2 e to the power xi square into d dx of this first function second function. So this will be first function second function, so d dx of first function into second function, so this will be minus e to the power xi square minus e to the power xi square minus xi into uh, minus 2 xi into e to the power minus xi square. Okay, xi square. So this will be minus 2 xi. I can take xi square common. So if I take xi e to the power minus xi square common, so cancel. So it will be 1 minus minus plus minus minus plus 2 xi square, 2 xi square. Okay, 2 xi square. And uh, is it correct? Any mistake? Have I committed any mistake? Let me check. Let me check once again. This xi square d2 xi square minus 2 xi square minus 2 minus 2, then d xi square d xi minus this xi square minus xi square. So okay, so I have committed some mistakes, I think. Oh, this is plus. Okay, this is plus, this is minus, so this is minus. Okay, this is minus, this is minus, so this is equal to this is equal to 4 xi square minus 2, 4 xi square minus 2. Okay, I have to check this calculation. Okay, somehow xi square by xi square d xi square. Okay, xi minus this minus 2 common, minus 2 common this, then d dx of first function into second function, first function into second function, then plus first function into d dx of second function, d dx of second function equal to minus 2 xi into xi square this. Okay, so then we get this, so we get the value of psi 2 xi, we get the value of psi 2 xi this. So you see, in this way we can find out the value of energy and corresponding wave function. Okay, so we can find out the values. So here we have obtained the values of psi, in terms of xi, but we can convert it in terms of x since we have got the relation. Okay, we can do that. Now you see what information we get from the energy expression. No? from energy equation what information we get. So in particle in 1D box, particle in 1D box or 3D box, 3D box, we get kinetic energy, we get kinetic energy, and that kinetic energy is called translational energy. That kinetic energy is called translational energy, because we are just considering the translational motion in particle in one-dimensional box or two-dimensional box or three-dimensional box. We are considering translational motion of the particle. That means particle is moving in this direction or in this direction or in this direction. Okay, so we are considering translational motion of the particle. So we get kinetic energy, no doubt, because potential energy is zero. Potential energy is zero. We get kinetic energy, and that kinetic energy is translational energy. But here, harmonic oscillator, okay, harmonic oscillator. Here we get the particle is executing simple harmonic motion, that means vibration. So here what we are getting? We are getting vibrational energy. Vibrational energy. Here we are getting vibrational energy. You know, energy of a molecule is the sum of translational energy plus sum of translational energy, rotational energy, vibrational energy, and electronic energy. We know this. So we are getting translational energy. Now we are getting vibrational energy. Okay? So we are getting vibrational energy here. That is one thing. Okay? Second thing, that is one thing. Second thing is vibrational energy is quantized. Vibrational energy is quantized. Quantized. Because we have seen V equal to 1, so vibrational energy is okay, half H omega oscillation. V equal to 2, vibrational energy is 3/2 H omega oscillation, and so on. Okay, since vibrational energy is quantized, we will have vibrational energy levels. Okay, we will have vibrational energy levels. Say this is the lowest level. Lowest level E. This is 0. Sorry, this is 0. This is 1. 0, 1. Sorry, 1. Say this is E naught. This is E naught. Half into this. Half into this. Okay. Then we have E1. E1. This is equal to 3/2. 3/2 into this. Okay. 3/2 into this. Then say E2. We will have 5/2 into this. 5/2 into this, and so on. So vibrational energy is quantized. That means the particle can have this much vibrational energy, or this much vibrational energy, or this much vibrational energy, but in between, no. Okay, so vibrational energy is quantized. So these are the vibrational levels. This is the lowest vibrational energy levels. Now, since vibrational energy cannot be zero, V may be zero, vibrational energy cannot be zero. Okay, so lowest vibrational energy is called the lowest vibrational energy is half H omega oscillation, and that is called the 0 point vibrational energy. 0 point vibrational energy. Okay, lowest vibrational energy is called the 0 point vibrational energy. V may be 0, but vibrational energy cannot be 0. Okay, lowest vibrational energy. So these are the information we get from the energy expression. But to get information from wave function, we have to plot wave function. As before, we have to plot wave function. So if we plot wave function, say when p equal to 0, so we get psi 0, okay, psi 0. If we plot, we will get function like this. Okay, we will get function like this. Against xi or x, nature of the function will be the same. We can plot the wave function. Now if we when p equal to 1, if we plot the wave function psi 1, if we plot the wave function, the function will be this. The function will be this, like this. Okay, function will be like this. Then p equal to 2, okay, p equal to 2 psi 2, the function will be like this. The function will be like this, and so on. Now, plot of square of the function is more important because square of the function gives the probability. So if we plot the square of the function, say sine naught square, the function will be like this only. That is, maximum probability is at x equal to 0. In 0 point energy level, the maximum probability of finding the particle is at x equal to 0, equilibrium position. Okay. Now here if we plot psi 1 square, so it will be like this. Okay, psi 1 square. Maximum probability here and here. Okay. Now if we plot this psi 3 square, so it will be like this. Psi 3 square. Maximum probability here and here. Okay. So you see, maximum probability shifts towards amplitude. Okay. So this is all about your particle one-dimensional harmonic oscillator. Let us stop here today. Next time we will discuss little bit more about harmonic oscillator. Okay. Then we will go to rigid rotator. Okay. So thank you.